Yep.
All right, so let's take a look at what we have here. It says if a horizontal force of P, 100 newtons, is applied to the 300 kilogram reel of the cable. Determine its initial angular acceleration. The reel rests on rollers A and B and has a radius of gyration of 0.6 meters. It resting on those rollers is... Oh, okay, I see what they're saying. So the rollers are going to be zero friction, but I shouldn't say zero friction. The roller is going to provide enough friction. All right, so get a pen. Got my pen. How thick is that? A little bit smaller. That's good enough. All right, so let me get my pens in order. I'll do blue and green and red. Purple's good, and orange. Those are great colors. Dope. So we got this force P. We got this force P, and we know that this P is going to produce a rotation. So if you were kind of look at how P would extend into the body looking at its moment, the P would produce a rotation that looks like this, right? So we know it's going to rotate. There's going to be a negative acceleration. So let's take a look at our free body diagram. I'm going to just use this object and then draw the free body diagram variables directly on top. So we have the weight pushing down like that. So we got our mass times gravity. Then we have, if you take a look, this bad boy is sitting on the rollers. And so the rollers have to be where the normal force are put in. Make some sense?
Yeah.
Okay. So with that being said, so we have the mass, the gravity, and the normal force. These guys are my action-reaction pair to the weight. All right. So I'm going to call it a normal A, normal B, because I don't assume... I actually have a feeling that normal B is going to be bigger than normal A, but I'm not sure. You don't assume what they are. You don't assume that they're the same, and you don't assume what they are. I've made that mistake so many times, and I still make it to this day. But we're just going to name them normal A and normal B and see what we can do with them.
Can we draw the actual free body diagrams just so I can see how to draw it? Because that's part of the reason why I was like, I wanted to do this problem.
Yeah.
Because like this.
So I would draw like
geometry of it was interesting.
I draw a circle, and then I draw the two little thingies. Technically, you don't have to draw those. Technically, the free body diagram is you're just drawing the object. I put the center of mass here, G. And then I would start adding on these bad boys. So I would say there's a P happening right here. And I have it come off. And then I'll put the arm associated with it. And so I'll say that that arm is 0.75. Okay. Because I need to know that bit of geometry because I know that's going to cause moment. I know that's the whole reason this thing is rotating. So I put that. I put my mass times my gravity. Then I put an A here and a B there. That's how I'm going to do that. Make some sense?
Mm-hmm.
Now, the geometry of it is going to be seen right here with that 20 degrees. So I'm going to do, it's going to be 1 with a sine of 20. So that's going to be my Y. That's going to be my Y distance. So I'll go like that. And I'll say 1 sine of 20. Or just sine of 20, really. Make some sense?
Mm-hmm.
Cool. So I know that's my, if I were to just kind of extend that up, I know that that's how that works. And I know it's going to be like that on both sides. So I have that. So I have action, reaction pairs. And now I need to also make sure that P has its reaction being considered. Because everything should have you got to always make sure that there's a reaction to your actions. There may be one. There may
not. The reaction for P would be the friction force, right?
Actually, no, because this isn't going to be moving. It's just going to be rolling on the. It's going to be rolling in place, if that makes any sense. Its resultant motion is going to be like this, just rolling in place. It's not actually going to be translating. So this is going to end up being a fixed axis rotation answer. Does that make some sense? The answer is a pure rotation. And so if it were moving, then yes, there'd be a friction. If it were sitting on like a horizontal surface, then yes, there'd be friction. Is there a point of friction on that block? Yes, but we're not going to consider it like that. Okay, we're not going to consider it to be friction. I see what you're saying. It's to say that put that as a force of friction. But what I'm going to do is I'm just going to call it the reaction on X, because the point of interaction right here is it's a point. And because of that, I don't necessarily know anything about it. It doesn't say anything about friction in this problem. You see that? This is nothing about friction.
Mhm.
And unless you know the material that this is made of, you have to know the material that this is made of and the material that's made of, and then the coefficient of friction between those two materials. And that's in some chart that they made forever ago. And you're never going to need to do it in dynamics. So if it's not mentioned, you're not going to use it. So what we're going to do is we're going to name it the reaction in the X direction. And we just need to solve for that. Make some sense?
Yeah.
All right, so we're going to put the reaction in the X direction on that guy. And it looks like it would only be on B, because the point, if you take a look at the way that A looks, since A is like that, it doesn't look like there'd be a reaction that would kind of point it like that. Since its weight is pushing down, you get the normal. This is pulling that way. And it looks like the only thing that would actually stop it, the reaction wouldn't be generated on A. The reaction will be generated on B, because B looks like it will be the only thing to kind of stop it from tipping over. Make some sense?
Yeah.
And so that's how I'm going to do that. So we have our free body diagram. I'm going to drop a kinetic diagram. Boom, boom. Put a circle. And
She normally just does MA for her kinetic diagram.
that's nice, but I like to be safe than sorry. Because the thing is, you have MA and then you also have I alpha.
IG, yeah.
The I alpha interacts with the MA actually. And so I only ever see it when it comes down to I do know that MA equals 0. MAX and MAY both equal 0. So I do know that. But I know that there's also an I alpha that needs to be considered here. I'm going to do, so here's the thing. Thinking about it. When you do I alpha, I'm just going to call it I alpha for now, and I'll figure out whether I want to use IG, whether I want to use IA, whether I want to use IB. Does that make some sense? Because you can choose the I that I can choose this point to be my I, this point to be my, this point to be my, or this point to be my. Does that make some sense?
It does. I never thought about it like that.
Yes, actually, if you choose the right place to be your I, it's going to mitigate certain variables out of the equation, and it's going to solve for certain things easier than if you don't. So choosing your I is super, super important. I will tell you this. The best place to pick your I, as far as I've come to understand and just kind of reading, and I'll put it in red. The best place to put your I is at the instant center. Instant center is the best place for I. Always. Because at the instant center, that's the one that's going to typically destroy the most variables and simplify your moment equation the most. So I will say that instant center is generally the best place for I. It's just that
There's no instant center in this problem, though, right?
I mean, there may be. That's the thing. I'm not sure, because there's no velocity to kind of figure that out. So, yeah. See, the thing is, you're right. There is no instant center in this problem, because there's no velocity that's been generated yet. And this problem, this thing is actually moving at 0 velocity right now. B equals 0 for this guy.
Yeah.
Because it's starting from rest. Because this is an initial thing. So it's going to have an initial angular acceleration, but it's not going to have any initial velocity. So because of that, there is no instant center. So actually, yeah. What I think I'm going to do is I think I'm going to choose this spot, but we'll see. I might have to use G. So I'm just going to kind of play with it really quickly. As I draw the equation, I'll figure it out a little bit more. So let's do our X and Y equations. Just because the mass times acceleration is 0 doesn't mean that you don't do an X and Y equation. You still do them. I'm going to say my coordinates are like this: X, Y, and Z. Even though that Z is technically backward, I'm going to do it like that anyway. And I think I'll put that in. Yeah, I'll put it in. I'll put a little purple on it, like that. All right. So let's see. We got positive X. We got our P, which we know is 100. 100. Then we have negative Rx. So now we know the reaction has to be 100, but it's got to be negative because it's backward, right? So that's that.
Mhm.
Then we have, now, of course, if you want to think about friction from here, you can, because you're right. There is going to be a friction associated with the normal of A and the normal of B in the Rx. So you can kind of use that later on if we want to do a little bit more thinking about it. We might be able to do even some sort of like back solving to try to help us figure it out, because this guy is rolling, and roll does come from friction. And so,
Yeah, because I know she tends to like to solve problems. Like some problems require like critical thinking in that sense.
yeah.
So I
So
was making sure.
we'll think about it as we go, but for now, I'm just going to leave it alone, leave it just like that. In the y direction, we know that 100 equals NA plus NB.
Mm-hmm.
So NA plus NB equals 100. Now, this does not prove anything other than that NA plus NB equal, not even 100, my bad, it's mass times gravity. Mg, and Mg is going to be 300 times, I'm going to use 10, so I'm going to say 3,000. All right. And then our Z direction. Okay, for the Z direction, we have, I'm going to use the force creating the positive motion. And so that's why I said down is going to be positive. Make some sense?
Mm-hmm.
All right, that way it's going to make my I alpha positive. I try to have my resultant motion be positive if I can. Sometimes you can't, but I try to have it be positive. So it's going to be P times 0.75. And then that's going to be 75. Then it's going to be, I'm actually going about G. Now that I think about it, I'm going about G. So we'll go about G first and see what G does for us. Hopefully,
That's your moment equation, right?
This is our moment equation. So I'm going to go about the center being G. All right, from here we'll do the mass times gravity goes away. Then you're going to have a positive NA times the sine of 20. Then you're going to have a negative NB sine of 20. Then you're going to have a positive Rx times by, see, I need this height right here, which would be cosine. Do you see it? You see the cosine I'm talking about? If I do a little triangle right here, notice that my triangle doesn't touch all the way. It's not touching the bottom. It's a little bit further. And I need, that's going to be my Rx. And so I need this distance right here, which is going to be 1 cosine of 20. Make some sense?
Yeah, why is it 20? I mean, why is it cosine of 20?
Because, let me go back. Because this angle right here is 20 degrees. So it looks like this. That's the 20. So I need the cosine of 20 because I want to get this section. That section comes from the cosine.
Okay.
Because I got X and I need this perpendicular, which will be that green line. Make some sense?
Mm-hmm. And then it's NA minus NB.
Yeah, because NA, if you take a look at NA, it's going to come up and around to create a positive, but NB is going to come up and around to create a negative. And so it's going to be NA and then the minus NB. All right, so we got that. Then we got to have plus, it'll be Rx cosine of 20. And then finally, so that's 1, 2, 3, 4. All right, finally, we're going to have IG alpha. So it's going to equal IG alpha, where IG is going to be mass times K squared. Is it mass K squared or 1/2 mass K squared? I always forget. We talked about
mass K squared.
Mass K squared. All right, great. So it'll be 300 times 0.6 squared. All right, dope. And then the alpha is, of course, unknown. That's what we're solving for. So I'm going to just put a nice red underline on this guy. So we're kind of in a weird place because we know Rx, but we have these guys missing. So I got to do some thinking to see if I can figure that out. So what I'm thinking about right now, and so what I'm thinking is these guys are
force.
Yeah, they're perfectly balancing the mass. And because they have the same geometry, it's a little triangle. So this would be the center of mass. This is in A and this is in B. And that's a isosceles triangle, which means that their components to balance the mass should be equal. They're balanced. So I'm actually willing to believe that they're both half, which means that it's just going to be n, which is equal to 3,000, which means that these two would actually cancel out on each other. How would I want to write that? I'll do something like this. And so they net out to 0. If that's the case, if they're equal to each other, then they'll net out to 0. They'll produce perfectly opposite moments, which means we get this. We get the moment produced by the P. The moment produced by the P combined with the moment produced by the Rx has to give me my resultant moment. And that just means that we only have these X forces to create this moment, which looks about right. So I'm going to go with that assumption. Make some sense?
Mm-hmm.
So this part right here, for me, in this problem so far, this part right here was the most confusing. That was the part that I had to take the most time to think about. All right. So with that being said, I can actually solve automatically for alpha. Alpha just solves out pretty easily. Alpha equals. Now here's the thing. This isn't always going to happen. Sometimes you do get a fourth equation. Now say you were trying to solve for NA and NB, right? Because that's going to happen. Sometimes you're going to have to try to solve for the normals. So say you were trying to solve for the normals and you needed I alpha. Say I alpha was the unknown variable. When I alpha is the unknown variable and you have like motion, you have like a motion to it, then you're going to use the friction. You're going to use the static friction value if it's rolling. And you have to solve for it. If rolling, no slip. You have to solve for it. But the thing is, if you're using static friction rolling no slip, then you're gonna know tangential acceleration equals how does it go again? Alpha times R. And so you'll know this. And so that's what you'll use to back plug. That'll be your fourth equation. If it's not static friction, then you'll be using kinetic friction. Kinetic friction comes from rolling with slip. Make some sense?
Mm-hmm.
And I don't know if she's spoken about rolling with slip versus rolling with non-slip, but that's so important. You have to make that assumption. You have to know which one it is. If you don't know which one it is, you have to solve two problems, one with slip and one with no slip, and see which one makes the most sense. Generally speaking, it's rolling without slip unless they say otherwise. Okay, so I always assume it's without slip until they say it slips, because slip is a little bit harder. So if it's rolling with slip, you're not going to use this. This falls apart. Excuse me. This right here falls apart when you roll with slip. When you roll with slip, all you know is this: that the force of friction equals mu k times n. So that's what you back plug. So you have two fourth equations that you could solve in tandem with these three to get you your answer. Does that make some sense? That's if you're looking for resultants, like normal forces or reactions.
So, okay. Static friction is what exactly? Because maybe I missed. I don't think she ever went over if it's rolling with no slip. So, like, I get that static friction is equal to that if it's rolling with no slip, like in the problem. But
no,
like,
you have to solve for static friction. You have to solve for static friction.
And
static
the tangential. Okay, the tangential acceleration is the static friction.
That's just an equation that you know from motion. So this is a motion equation. We just know that because of when it's rolling with no slip, it's following the regular rules of Jesus, what is it called? Fixed axis rotation. If it's rolling no slip, then it's going to be a fixed axis rotation. And if it's fixed axis rotation, then we know that about the motion. And that's what we learned before when we were doing the stuff.
But it's kinetic. It means that you're saying that it's a translational motion. It's kinetic friction.
Yes. So when it's kinetic friction, it's no longer fixed axis rotation. It's general plane motion.
Mm-hmm.
and you can't look at it as a fixed axis rotation. That's the cool thing. When it's rolling with no slip, yes, it's technically moving with general plane motion, but the no slip condition means that you can use the method of instant center. And because you can use the method of instant center, you can take a picture of the situation and evaluate it as if it were fixed axis rotation. So it simplifies. But when it's rolling with kinetic friction, which means that the wheels are slipping, the speed of the wheel and the speed that it's moving along the ground, so the rotation and the translation are not connected. That's the thing. When you're rolling with slip, the rotation is connected to the translation by the fixed axis rotation. We can prove that a little bit later, like mathematically. But when it's rolling with no slip, when it's rolling with slip, they're not connected anymore. That's why when a car is skidding, the wheels are moving fast, but the car's not going anywhere. That's the exact way that you have to think about it. The wheels are literally slipping on the ground, and because they're slipping, the car can't move forward. So the car can have a very, very, very small translation and a huge angular motion. That's what happens when you roll with slip. And that's why the only thing that you know about the slipping is that kinetic friction is the only thing that's that's the only force that's being generated is kinetic friction. And so kinetic friction governs slip and static friction governs no slip. The moment you overcome static friction, your wheels start to slip. That's why you can't rev the gas too hard when you're coming off the block with a car. If you rev the gas too hard, then the force that your car produces overcomes static friction and it becomes a kinetic friction, and then your car can't move properly. Now, all of that was an extension because I noticed that we don't need any of this for this problem, but I will say some of the more traditional problems do end up using one of those two bits of information. What we can do here is just solve this.
There's another problem. There's another problem that uses it in this.
Perfect.
In that document I sent you.
Okay, perfect. So yeah, we'll just throw this together. So we'll have our 75 plus which actually ends up being negative because I didn't realize that Rx is, hold on now. Oh, silly me, not negative. I didn't need to put a negative there because I have it drawn properly. It's positive. All right, so I got 100 times cosine of 20. What number is that? 20. It's 93.9. Divided by mass, so 0.6 squared.
Where you get 3,000 from? You got 3,000 just because you
I rounded the gravity. I rounded the gravity into 10. That's my thing. I round gravity into 10 so that whatever number the mass is, I just multiply by 10.
Okay.
So 108, and that will be our answer. So we got a 75 plus 93.9 divided by my last answer, which is 1.56-ish. So our answer is roughly 1.56 radians per second squared. And that will be our answer. Does the method that we just used make some sense?
Yeah, I'm trying to figure out where you get the 108 from.
Oh, the 108 is this.
Oh, okay.
Calculator real quick.
Okay.
So yeah, that's that. Questions. What's going on? This part right here is our bread and butter. So it's generally going to be build the system of equations and then use a condition of motion together and then solve a system of equations. Generally, that's the way it is. The hardest part is making sure that you build your moment equation and picking the right point to build it. In this case, using it around G was pretty easy. So that worked out pretty well.